So I'm Kev, and I'm going to talk about eBPF. But first, isn't it nice to be back at a conference after the lockdown? And I don't know about you, but I really enjoyed the lockdown because it meant I got to stay at home. And I did some crazy things. So I built a bookshelf door for my spare room, because what else do you do? I bought some incredibly expensive art, which is basically a riot shield that Jimmy Courtney has acquired from the police and then painted up. Jimmy Courtney being, of the KLF, who once burned £1 million, and they were selling these at Banksy's Dismal Land originally. So I kind of hope it's a Banksy, but you never know. And I also took advantage of the lockdown where all university teaching went online to convince my hero, Zoltan Dienes, to take me on as a student in a master's degree in psychological methods at University of Sussex. So I'm doing that part-time. I'm halfway through a master's, which is quite nice. I also got married, and with my... Thank you very much. And with my wife, we started a blog called Cosmic Pancakes. The URL is cosmic-pancakes.com, and it's all about hypnosis. So come for the sarcastic book reviews and stay for the science, or come for the science, stay for the sarcastic book reviews. But anyway, you can find me on Twitter. If the Kev security handle is the one where I talk about eBPF. The other one is where I rant about politics and talk about hypnosis. So feel free to follow whichever is most applicable. Right, so I'm going to talk, about eBPF. Mostly it'll be about how it works and why it's a bit difficult to use, but why it's really incredibly useful, and a little bit about how it's vulnerable, but we'll come to that. So if you've used T-Shark or Wireshark or any libpcat-based thing, you've used BPF, Barclay Packet Filter, because that's how capturing packets works on Linux. If you were designing a packet capture thing, where the kernel's got to do with capturing, you could build a configuration language and build that into the kernel, and you could send a configuration into the kernel, right? But you'd only be able to capture things that the configuration language knows about. So, if you wanted to add the ability to capture something new or a different way of filtering stuff, you'd have to modify the kernel. And of course, that takes time, and then it's only available on the new kernels. It's not necessarily available on the kernel that you're trying to capture on. So instead, what they did was they built a virtual machine inside the kernel, which runs BPF machine language. It's like bytecode. So when you put in your filter, T-Shark, -i, NE, not port 22, it compiles that as a BPF program and inserts that into the kernel. And then every packet that comes by gets shown to that program, and that program just says, yes, send it to user space, or no, don't send it to user space. And that's how the packets come out of the kernel via libpcap and end up in your tool. So eBPF originally was called extended BPF, and the idea that you could take that idea and use it in other places. But it no longer stands for anything. It's just a term, and it's got a nice logo, which you'll see everywhere. But I'll talk about what that is now. It's the same concept of running code inside a virtual machine inside the kernel, a bytecode basic virtual machine. It's just that instead of attaching that just to the network stack where it can see packets, you can now attach your programs to anywhere in the kernel. So practically any function call. Inlined ones, obviously not, but there are still ways. Practically any part of the network stack, any syscall, any trace point, of which there's loads. And you can essentially instrument what's going on. So you can write code that gets fired when a certain action occurs in the kernel, and you can see the parameters that are available at that point. You can reach into data structures. You can pull all sorts of information about the process and other processes. I'm going to say, so why would you want to do that? Well, you've probably used strace, that traces system calls that a program uses. And which is kind of useful if you're trying to debug something or you're trying to work out the flow of something and how it's interacting with the kernel. Well, you get a lot of data back, right? And sometimes a lot of that data is not very useful. But it also doesn't give you back any more data than the program knows about. It's basically just arguments to syscalls. So instead what you can do is use BPF to write a better S-trace, an S-trace that's targeted at what you're trying to achieve. It could ignore a whole load of syscalls until something specific happens, at which point it could then start reporting data. The data it reports, it could reach from inside the kernel and pull back. It can get stuff from the task struct, memory maps, all sorts of things. Using uprobes, you can snoop on user land stuff. So you can snoop on read line and get back every command line typed in bash, including passwords. You could snoop on OpenSSL read and writes if you're attached to a program that's got OpenSSL in it. So if you've used ptrace to build debuggers, or you've used GDB to attach to things, you can do those kind of things, but without the hassle of using ptrace. It's not detectable in the same way. It's probably detectable in other ways, but it's not detectable in the same way, which is always good. But it's a lot less clunky. Like the program doesn't necessarily need to know that it's being ptraced. Beyond those kind of things, which are kind of cool, you can also do container networking. So I work for a company called iSurveillance, and we make Cilium, which is an open source project at the CNCF. If you use Kubernetes, you might want your networking to be quite quick. Well, Cilium is dedicated to that, so firewall and load balancing and routing of packets and things like that. We also make Tetragon, another open source product, again in the CNCF, which is a way of logging data. And ultimately, one day that will replace Audit D, if you believe me. But you should believe me, because I'm going to make sure that happens. But I'm not really going to talk about those products as they are. You can go and get them from GitHub. I'm going to talk about the technology underneath them. Sysmon For Linux. I used to work for Sysinternals before I worked for iSurveillance, and I ported Sysmon from Windows to Linux. And if you don't know Sysmon, it's a tool for monitoring stuff on Windows. It's got two components, like a service and a driver that runs in the kernel. So I ported the service from Win32 to C on Linux, which has its own challenges. But what was interesting was, instead of using the Windows driver, I built a replacement for that using eBPF. So it picks up the same kind of data and sends it. As I say, it needs developing further, because I then left Microsoft and joined iSurveillance. But it is an open source product. It's out there on GitHub. If you use it or you like it, please feel free to extend it. Mark Vasinovich would love you to do so. And finally, rootkits. Building them and detecting them. There's a guy called Linux Thor. I've seen him speak, and his stuff is quite interesting, so I suggest you have a look. So I'm not going to talk about Cilium and Tetragon in too great detail. I just want to give you some idea of what BPF is capable of, what the power is of using it. So if you're using Kubernetes and you're routing packets, you're usually using, say, IP tables or something like that. As you increase in the number of nodes, there's overhead that mounts up. If you're using BPF to do your routing inside the kernel, so it doesn't have to come out of the kernel into user space and task switch and everything else, then you don't get that building up, and you pretty much have a constant, a constant overhead. To put that into a different type of graph, if you use an IPVS, for example, we get more packets throughput by staying in the kernel, and we use a lot less CPU. So it's just to give you an idea that eBPF is more than what it lets you do. It lets you do things fast, which is really useful. And Tetragon, to put it into context, is the thing that I work on, which is the observability part. It can attach to all sorts of things. If you want to do the BPF type things I'm going to talk about in this talk, but you don't want to write code, you can get Tetragon, configure it with a YAML file, and it will connect to the functions in the kernel for you and report the information you ask it to report based on it matching certain parameters that you've told it to match on. So you can get the power of BPF observability, but without having the hassle of writing the code and trying to get it to run. Because we've done that hard bit for you. and providing it as a way that makes it a lot easier to use. If you want to play with any of these things, we have free labs. It costs you an email address, basically, but come and see our labs and get hold of the technology and see how it works, where someone's already set it up for you. Right, let's talk about technology. So BPF is basically a risk language. It's got a stack of registers, and it's got basic operations. And that, as I say, runs in a virtual machine. The memory model, however, is quite interesting. There is 512 bytes of stack, which isn't a lot. But then we're not really doing function calls, so that's kind of the stack for your local variables, pretty much. There are no globals, and there's no heap, which sounds like a really difficult thing to program, and it can be. But what we have are BPF maps, and maps are places to store data. And there's lots of different types, but the most common ones are like an array and a hash. So all you have to do is define maps, and then you're essentially defining memory. And then you can access that memory, and you can play with it. So if you need a load of heap, you just create an array that's got one element in it, and that's the size of the amount of memory that you need. And then you ask it for that entry of that array, and that'll give you a pointer to a chunk of memory. That's essentially your heap. So you can then play with that memory as you like. These maps are shared between programs, and they're shared, if you want them to be, and they're shared between kernel and user space. So you can stick stuff into a map because you've observed something, and user space can read that out, like poll it periodically, if you wanted to. There's also a ring buffer map, so you can stick stuff into a ring buffer, and it will pop out in user space, where you can, or pop out in a different program. So there's some interesting things you've got to get your head around. I talked about trace points. So if you don't know, if you go to syskernel debug tracing events, then there's a whole load of directories, pseudo directories, which represent classes of trace points. And there's some quite interesting ones there, as you can probably see, that you might want to attach to. Like raw syscalls is at the start and end of the syscall architecture. Every time a syscall is made from user space, you will hit these trace points. Each syscall has its own trace points in the syscalls directory. Shed is about starting up processes, task switching, signal, sending and receiving signals, etc., net for the network. There's a whole load of trace points littered across the kernel, and they're really easy to attach to. So if you wanted to attach to, for example, this is sysenter exec.ve. Exec.ve is the syscall for starting a program. The enter part means just before it happens, so at the point they've called the syscall. There's also an exit one for after it's done its work. So you go into its pseudo directory, and there's a file called format, and if you cat that, you'll get this data. And the first chunk, which makes up 64 bits, is opaque, inaccessible, you can't touch. So you just have to know that it's there. But the rest of it are the arguments to the syscall, the arguments that the user space program called it with. So, there's also a syscall number, which is handy because you might want to attach the same program to lots of different syscalls, so you could check the number to see which one you've been fired off, right? But apart from that, it's just the parameters. There's a file name to run, there's an argv, and there's an env. So what you could do is smash together a struct that follows that format, literally sort of copied across. I've actually added a pad 2 in there, but you wouldn't really need, that's just to force the alignment, but you wouldn't really need to do that. And then when your program that you've attached to this trace point gets fired, it will get an argument, and that will be a pointer to this struct. And you can just reach into that struct and get those parameters. If you look at a non-syscall trace point, it's exactly the same kind of thing, same kind of layout. This is in shed process exec. So this is a trace point that gets hit when a process is executed by like exec.ve, for example. And you can see that the parameters there are a file name, the process ID, and the old process ID. Except you'll notice that the file name is only 4 bytes, which is too small to be a pointer. But it's a data lock. So basically, the data lock tells you where to find the file name. And it's kind of like a 32-bit number. The first 16 bits, or the lower 16 bits is the offset, the upper 16 bits is the length, right? And it's the offset from the start of that struct. Now, you'll notice I've put in an unsigned char raw 4K chunk at the end. If you don't have that, you get the data lock, you work out the offset from the start of the struct, it's pretty much going to be, like the offset is going to be to the end of that struct. And then you start trying to read that memory, and eBPF tells you you don't own that memory, because it's clever enough to know that the struct size prohibits you to reach that point. So you have to stick in some dummy buffer at the end so that eBPF knows that you own the memory so that you can actually access it. So it's a little bit of a trick, but I wanted to sort of mention that. But again, you can pull out these parameters. The difference here, of course, is we're in a trace point after the sys call has been called. So there's a good chance, you'd have to check the source actually, there's a good chance that the file name at this point is after the kernel has copied it. So you could trust that buffer as being a kernel buffer, as opposed to a user space buffer, which might change between the sys call being called and your program looking into that buffer. If you're interested in that, it's called Phantom Attack, and it was in DEFCON 29. It's worth looking up, because changing buffers from user space before the eBPF tracer sees what's in the buffer and changing it back for when the kernel gets to see it is quite a neat trick, and the guys managed to make that quite reliable. If you want to connect to an arbitrary kernel function, you can use a kprobe, kernel probe. And in this case, we want to connect to _ shed fork, which happens obviously as part of forking. You can see that it's got parameters of clone flags and a pointer to a task struct. Now, it's not quite as straightforward. Basically, your kprobe will get a pointer to a struct, which basically contains the registers that the machine has at that particular point in time. So imagine the machine has stopped, and you've now got access to its registers. But we know, the calling ABI in Linux, like the first register is RDI, the first parameter is RDI, the second was RSI, etc. So you can pull your parameters out of those registers. So how do you go about inserting code? Well, you write program in C, pretty much. You could write it in BPF assembler if you want, but most people write it in C. Compile it with Clang with the BPF target. That gives you an elf object, and then load that using a loader library, and attach it to a point in the kernel. And there are choices over loader libraries, so libbpf is the common one. Excuse me. Isovalent, we make one called Cilium eBPF, which you can get from GitHub, it's free, which is all written in Go. I made one at Sysinternals, which is based on libbpf. And once it's loaded into the kernel, you can get, it'll run, your code will run every time that attachment point is hit. So if it's a kernel function, every time that kernel function is hit, your code will run. If it's a trace point, every time that trace point is hit, your code will run. And then to get data back out, you can sling it into a ring buffer, and it will pop out in user space, and your controller that loaded it can get access to that data. Or for debugging purposes, there's a trace pipe where you can just print K stuff straight into, and you can just cap this trace pipe from user space, which is great for debugging, not very good for production, because it's one pipe that everything kind of basically uses. But if you just want to do some printf style debugging, which is the only way to debug BPF, I might add, then it's kind of handy. Now, you can't run kernel functions from within BPF. So it's not like a kernel module in that sense. So if you wrote a kernel module, you can pretty much run any function in the kernel. But the problem you've got running a kernel module is that if you make a mistake, your kernel crashes. Well, with BPF, that shouldn't be the case. If you make a mistake, your program should never get into the kernel in the first place. I'll talk about verification in a minute. But you can't run kernel functions. But what you do get is BPF helpers, of which there are loads, right? But some useful ones is getting data in and out and deleting it from maps, accessing memory, so you can safely access memory that you're allowed to access, perhaps, and dumping stuff out, as I said before. You can get interesting information about the process that you're running on. You can get information about the task that has been stopped, including its task struct. And if you don't know about the task struct, you go to elixir.bootlin.com, and you can look at the task struct and find that it contains everything a process needs to know about itself, all its metadata, with links off to its file descriptor table, links to the file system it's mounted on, memory, creds, the works. So if you can get a pointer to the task struct using BPF get current task, you can manipulate that task struct to get useful information. So you can get information on the helpers by doing man BPF helpers, and look it up. And then there's a load of links there for the kind of projects I've mentioned. Right, let's talk about what's difficult, because it makes it sound so easy. When you load your program, it goes through a verification process, a verifier in the kernel, and it verifies that your program will stop, and it will stop within 1 million instructions. On older kernels, 4,096 instructions. So it will try all the different branches of the program and check that you're not doing anything dangerous, like accessing memory you shouldn't be able to access. In some of these cases, looping, when you shouldn't be allowed to loop. Before kernel 5.3, you weren't allowed to loop. You couldn't mix function calls with tail calls, on certain versions, and you couldn't sleep, which I'll talk about in a moment, because that's interesting in its own right. If your program passes verification, then it gets attached to the point you want to attach it to in the kernel, then it runs. Most of your time is spent trying to make your program satisfy the verifier, to make sure the verifier is happy with it, which can be a not very enjoyable process some of the times. But the more you do it, the better you get, so fair enough. Sort of things, as I say, you can't access memory directly like you would if you're a kernel module. You have to use these helpers, BPF probe read and BPF probe write. Not every BPF program type, of which there are many different program types, can access every kind of helper. So depending on where you attach and what kind of attachment you want, will constrain you as to what you can actually do. So choosing the program type is kind of key. If you want to look at packets, then there are SKB, socket buff type programs which get better helpers for reading out packet data. The SKB load bytes will read bytes from a packet. If you're attaching as a K-probe, for example, you can still get access to that socket buff, but you're now using BPF probe read to read the memory, and the packet will be aligned and laid out however the SK buff is laid out, not linear as it would be if you're using like SKB load bytes. So you get more flexibility with the K-probe, but you lose some of their useful helpers. So there's trade-offs and choices to be made there. But basically, if you try and do anything the verifier doesn't like, it just bans your program and tells you no, you can't have it. And that's mainly there to make it safe. The idea is, it's not really a security boundary, it's more of a safety boundary. The idea is to try and stop you doing something silly, rather than trying to prevent you to doing something that could compromise a process, or compromise the kernel. Memory access, one of the things it does is it checks what you can read. So if you have an array, like in example here, an array of 6 elements, and your index is just an integer, well, theoretically, that index could be any number you like. It could be 27, it could be 200 million, right? So theoretically, you could access memory that you're not allowed to access. So the verifier doesn't know how you're using that index very much. It just knows there's an index. So it wants you to constrain that, like, forcibly. And one way to do that is to make your array a power of 2 in size, and then just mask off that index immediately before you use it. Now, in some situations, you'll run out of registers, like especially you're compiling C, right? You'll run out of registers, and what will happen is Clang will put your index on the stack, and then go off and do other things, and then retrieve it from the stack. And in certain versions of the kernel, the verifier didn't follow those elements after they've gone to the stack and come back. So you constrain your index, like here and 7, we bound it so it's got only values between 0 and 7, and then Clang sticks it onto the stack, and then when it comes back off the stack, the verifier thinks, well, that's a completely unbounded index. That could be any number you like. So sometimes you will find Clang's done something stupid, and even though your C code is right, you can't get Clang to make code that the verifier is happy with. The solution is inline assembly. So not only are you fighting with a verifier and trying to do difficult things, you're also now rewriting your C as assembler inline in your program in order to force Clang to do the right thing at the right point and not spill the registers. So it can, as I say, it can get a bit tricky. I mean, loops. So before 5.3, you weren't allowed any loops. And so all you do is just unroll them in Clang. And Clang will just like unroll the loops for you and make it big. And Clang is quite good at unrolling loops. But once you get to version 5.3 of the kernel, like, you can have loops. So why don't you use them? Well, you do, but you have to be careful because the verifier is not that smart about loops. So it likes ones that are simple for loops, like following an index. But if you start sticking complex terms in the test for the loop, it can't rationalize what you're trying to do there. There are too many paths appear, it becomes too complicated for it, and it basically gives up. So instead, you need to make your loops simple and break out of your loops using break statements. It makes you write more bulletproof code and easier to, if it's easier for the verifier to rationalize what's happening and reason about what could go wrong or what could happen, then it's going to be easier for you to do the same. So you essentially write code that probably has fewer bugs because you can actually see what's going on, rather than trying to write fancy, clever stuff that takes up less space. Let's talk about sleeping. So I didn't know anything about sleeping until I got to BPF, but what normally happens when your program tries to access some memory, and that memory is not paged in, is it tries to access a memory location, an interrupt fires, the control gets passed over to the kernel sees that you're trying to access a particular memory location and it's not paged in, pages the memory in for you, and then returns from the interrupt where the instruction that you've just run runs again, and then but this time the memory's there and it gets the piece of memory it wanted. To the program, it's completely unaware that this has happened. If you timed things, you could spot when it happens and when it doesn't happen, because obviously there's a time element to this. Very small, but there's a time element. Before 5.10, when they introduced sleeping programs, it basically, you tried to access the memory, like BPF probe read, and it just went, no. No, you can't have that. Give you back an error message, and the memory you've asked for is all zeros. So this is a problem usually when you're trying to read user space memory. So for example, if someone is, if you're attached to the open syscall, which is the sort of thing like a normal tracing program, like audit D, K-audit does it. There are other tracing programs like Tracy and Falco and things like that. If you're attached to syscalls, which is the normal thing to do, like there's an open syscall for opening files, there's a, write, read, things like that. In that open syscall, one of the parameters is the file name you're trying to open. So it would be logical for your BPF program to read that and report it. I mean, as I say, it's a user space buffer. So because of the phantom attack, what your program sees and what the kernel sees might be different due to timing and stuff. But assuming it's correct, you try and read that buffer, it might be paged out by the time your BPF program runs, because the kernel might need that. Your process, your other processors might be busy using all sorts of other memory. So the trick I found, if you happen to want to do that, is on the entry point to the syscall, so sysenter open app, for example, store the pointer to that user space buffer in a map, and then on the exit to that syscall, have another program that runs, which retrieves from the map that pointer and then reads the memory, on the basis that if the kernel has just read that memory in order to open the file, it's probably still paged in. Not foolproof, but is better than nothing. What's a better solution, of course, is sit on the exit of open, where the return value is a file descriptor for the file, and then instead go into the task struct, find the file descriptor table, and then find the file descriptor in the file descriptor table, and that will point you at an inode. And that inode will have a directory entry, and that directory entry will have the name of the file. Obviously, it'll only be the actual name of the file, not the directory it's in. For that, you'd have to look at the parent entry and get the name of the parent, the directory it's in. But of course, that's just that part of the file path. So you'd have to map, you'd have to recurse continually in order to get the full path, like directory by directory. And of course, once you get back to the root directory, you might not be at the root, you might be on a mount point. And then you have to look at the mount point and see where that's mounted, and then do the same process again to map all the way back until you get a full path. And of course, the path could have 2,048 directories in it, technically on Linux, because a path name could be 4,096 characters long. So how are you doing that without loops? Or even with loops? It's quite a tricky thing to do. It uses a lot of instructions, and you hit that million instruction count really quickly. So there are some difficult things, but it swings and roundabouts, In 5.7, they added some new helpers, which make life a bit easier. So if you're running code on 5.7 or later, brilliant, use the helpers that are available. But it's one of those things, if you're building an observability program, what are you running on? Well, you're running on whatever the user is running on, and that's basically whatever's deployed. And people are running some old kernels out there in the wild. Tetragon, we support back to 4.19. I think Cilium supports back to much earlier kernel, like 4.4 or something, because that's what people are running. So it's nice that new helpers appear and give you more functionality. And you could have versions of your programs that use those when they detect a kernel that's got them, but you still have to work for the lowest common denominator, which are the smaller set of helpers, the more difficult kind of set. So that in itself is a bit tricky. This is just something I discovered. I probably wasn't the only one to discover it. It's just amused me that when you send data into the ring buffer, it's using a U64 to specify its size, which is huge, huger than anything you can possibly imagine. But otherwise, it was a U32, and the U32 is like 4 gig in size. Yeah, okay, fair enough. That's really big still. But it goes through the perf subsystem, and in the perf subsystem, that's a U16. So if you try and send in more than 64K of data, what actually happens is it sends all of the data that you have put in, but the pointer in the ring buffer is only advanced by less than 64K, like by whatever it is after it's been masked off. So if you send in 64K and 8 bytes, the pointer would advance by 8 bytes, even though this whole 64K and 8 bytes is in the ring buffer. And therefore, the next sample that arrives in the ring buffer will overwrite. So unless you get it out fast enough, it constantly gets overwritten and corrupted, which is just hilarious. On top of that, it's not exactly 64K because there's headers in there as well, which you aren't aware of, and you can't easily find programmatically which headers will be in there and how big they are. But they're about, between 8 and 48 bytes in size. I usually assume, say, 64 bytes. So you think 64K is a lot of space. It's not if a command line can be 128K. So what you need to do is chunk up your data, send it in packets. And to be honest, there's really good reasons for chunking it up anyway, because the ring buffer can get saturated. And when it gets saturated, it will just drop those samples, those events, which obviously you care about those events. You've sent them to user space, you want to read them, right? But if too much is happening and you're not reading it out fast enough, or the ring buffer's not big enough, you lose events. So if you chunk up your events into smaller packets, one, it makes it much more efficient anyway, and therefore it's quicker to read stuff out. But two, imagine if your event, instead of being one big sort of, I say packet, but one big struct, Instead, which could get lost, it's 8 smaller ones, which are numbered and could be reconstructed in user space. Well, if one of those 8 doesn't arrive, you know it's not arrived, but you still have some information about the event. You still know the event happened, like a process was executed, a process forked, or whatever. You just might be missing some of the data. If you miss the entire event, you don't even know it happened, right? All you know is that you've lost packets, that's it. Other interesting things, the kernel structs, which you really want to get access to and read stuff out of, change kernel by kernel, right? And they also change configuration by configuration. So depending on how someone's compiled their kernel, the structs will be different layouts to what you're expecting. And the way to get around that is a thing called BPF type format, which describes the kernel. It technically arrived in 4.18, but it wasn't enabled in any distribution by default until Ubuntu 2010. Now it's becoming quite common to be enabled because it's really useful. It tells you about the size and shapes of structs, so you can learn about them, so you can access them. But there are other ways of acquiring that data. We have in Cilium eBPF, we have a means of getting that BTF data. Aqua built BTF Hub, which has databases of those layouts available on their website, and your program can go and get that programmatically based on the kernel version, assuming it's an off-the-shelf distro. When I was at Sysinternals, I built one into the Sysinternals eBPF library. So that tries a few different ways of getting that data. It doesn't get the whole BTF, it only gets the data that I cared about. So you'd have to manually extend it. But one of the ways it did it was, like with BPF, you can read memory from the task struct. So what I did was I dumped the task struct from like a BPF program, and then into user space, and then I hunt through that for information I know. So I know the PID and TID, because they're my PID and TID, right? So I can hunt for that in that space. When I find it, I now know the offset to the PID and TID. I know roughly what comes before and after. I can detect a pointer. And if I detect a pointer, I can ask my BPF program to dump memory from that pointer. I know my credentials, so I can hunt for the credentials in it. And so basically, I did memory forensics using BPF in order to understand the layout of structs, in order to make my BPF programs know where to find stuff. I mean, it's a bit cavalier. And when I told Mark Rusinovich, he said, that's how I do it in programs on Windows anyway, so that's a perfectly reasonable way of doing things. So it's not as mad as it sounds, but when you look at it, you'll think, how could that ever work? Licensing is something that you'll probably need to overcome if you are going to use BPF. So the helpers that you want to use are GPL2 licensed. Now, so there's this thing I've never seen before in the world of licensing. Every BPF program has to specify its license in the code, in a section in the ELF, right? I've never seen that before. And what happens when you load your program in is it takes that license and then it decides which BPF helpers you can have based on what license your program is running. So if you say, I'm MIT, it's like, great, of course you can run, but you can't have BPF probe read, because that's a GPL2 helper. So you basically have to license your program as GPL2 and specify in the code that it's GPL2, not even in the documentation. So as a result, your code will probably be GPL2. LibBPF and Sysinternals eBPF are both LGPL 2.1, which are allowed to load GPL2 programs into the kernel, and you can dynamically link to that from any license of program. So you can write something that's MIT or Apache, and you can, or bespoke proprietary licensing, and you can dynamically link to LGPL libraries that can then load GPL programs. I know this because I asked a lawyer when I worked at Microsoft, and this is the advice that I understood them to have said. Obviously, I can't say that in any more strong terms than that, but this was my understanding of what they said. And I'm not a lawyer, so do get your own advice. But if you're releasing code, you might want to think, rather than you could just GPL2 everything, and then you're definitely safe, right? But if you don't want to do that for reasons, you might want to think about this. Because obviously, if your code's GPL2, and you're delivering it as a binary, anyone could ask you for the source of that program, which could have some ramifications or impact on your commercial future, I guess. So vulnerable stuff. I'm not going to go into vulnerabilities per se, but if you look up on one of the CVE databases, you'll find there's quite a few vulnerabilities related to BPF. And most of them are related to libbpf, like the loader library, and it's just the normal everyday bugs. No one really cares. Like you'll probably root anyway before you load it, so like if you compromise a library in your root, you're still root. It's not really that sort of horrible or damaging. The more interesting bugs, and the ones that I think are worth reading about, even if you don't care about BPF, but you just want to read about a really cool bug, a really cool vulnerability, are some of the more recent ones to do with the verifier. So the verifier checks all of the code before it loads it into the kernel. That's what we understand. However, it also tracks the state of variables, and if it thinks a variable can only be 0, and you have an if statement based on that variable, it will only verify the path of the side of the if statement which for when it's 0, right? So if a equals 0, do x, y, z. Well, it will verify that, but it won't verify the else clause because, as far as it's concerned, that variable can only be 0, so it's never going to look at the rest of that code. And it needs to do that for practical, pragmatic reasons because it needs to reduce the amount of work it's doing so that it happens quickly, etc. Well, what some very clever people discovered was that because of bugs in the verifier, you could get a 1 into a variable when the verifier thinks it's a 0. Now what it means is it verifies the part where it thinks the path based on the variable being 0 and ignores the other path, which can do horrible, damaging, crazy things. And then when your program runs, actually that variable is a 1, and you go into the unverified path where you can do what you like, read any memory you like, etc. It's a logic-driven bug or logic-driven exploit, and it's not like anything I've read before. So I found that interesting to read, even if you're not interested in BPF, it's worth a read. So that's the reason why I wanted to briefly talk about vulnerabilities. The other thing to say about vulnerabilities is you'll hear people say, there's vulnerabilities in BPF. There are, right? But running BPF programs doesn't make you any more vulnerable. Like the vulnerability is in the kernel. It's if your attacker is on your machine as root and they run a BPF program, they might be able to compromise the kernel. That's the vulnerability. So don't not run BPF programs because there's a vulnerability, because it doesn't make you any more vulnerable. What makes you vulnerable is having BPF turned on in the first place. But if you want to do packet capturing and you want to run any of the cool stuff that's coming out today, you kind of need BPF turned on. And you will find BPF is on by default in all the major distributions and has been for years. So those vulnerabilities already exist. So the only thing you can do is patch your kernels, apply your patches, upgrade your kernels, use more recent kernels, use less buggy kernels. So that's basically what I was going to say. It's an amazing technology. It lets you run code in a place where unless you're writing kernel modules, you've probably never had the opportunity to run code before. And with that code, you can reach parts of the system that you probably could never observe before. And you can do that lightningly fast in a way that we've never seen before on Linux. It's regarded as the biggest change to an operating system kernel for 50 years. It's massive. And we're just going to see more and more of this, and you're going to hear more and more about BPF and BPF-based tools. So with that, I know the first question is always, can you give me those links again? So I'll say, any questions? Huh?
Sorry, can we have hands up for questions?
I'll be around. I'll probably be in the bar. Feel free to come and hassle me. Oh.
There's a couple of probe vendors out there. Are you going to be having a conversation with them?
Is it who?
A couple of probe vendors out there.
Oh.
Are you going to be having a conversation?
I might go and ask them what they're up to, yeah. I might sell them something, you never know. Nobody else? Then I must have done a fantastic job. Thank you.